So, it's March-April time, which for us in the Northern Hemisphere means we're emerging from the dark of winter and into the longer days of summer. Hallelujah, I hear you shout. Well, for most people, that is the reaction. When I was working as a maintenance manager, I had mixed feelings about this time of year. Summer means heat, and heat and railways don't always mix well together. So, as a maintainer, the back end of winter and the start of spring is the time to get your area of railway prepared for the summer months. Getting it right now can be the difference between a summer of high worry and stress and a summer of moderate worry. Summer prep is a critical yearly activity, but what does it entail? Let's find out. The hot weather affects many different parts of the railway, from causing the overhead lines to sag as they expand, or other equipment to fail due to overheating. However, the biggest risk, and therefore the area that gets the most attention, is track buckles. Track teams will spend this summer prep time looking at key parts of the track to ensure that they are ready to withstand the rigour of the hot summer. So what are these areas? In this video, we'll have a look at a few of them, such as ballast profile, adjustment switches, rail stress, joint gaps, and other mitigations that can be taken. First up is ballast profile. The stone you see spread across the railway is known as ballast. It provides a number of functions to the track system, but a key one is resistance to lateral and longitudinal movement. It achieves this by creating friction against the sleeper surfaces, as well as by adding mass that has to be displaced for the sleeper to move. For the ballast to provide maximum resistance, it must be at the correct levels. This is known as ballast profile. The bays or beds between the sleepers need to be full and the sleeper ends covered. In the UK, the profile of the ballast, or the shoulder, at the sleeper ends differs depending on the track construction type. For jointed track, the ballast needs to be level at the top of the sleeper. For continuously welded rail, CWR, it should be 125mm high and 450mm wide. It is also important that the ballast is clean, meaning that it's still angular and free of fines and dirt. This allows it to interlock properly. Degraded ballast or areas of wet beds, as shown in the picture, provide less resistance to the movement of the track. These areas have to be logged for additional mitigations or removed before the hot weather. For more on ballast, do check out my video on the functions of ballast. Hit the link in the top right of the screen now. Adjustment switches. Adjustment switches, or breathers as they are sometimes known, are a scarf type joint that is installed between CWR and jointed track to allow the CWR rails to expand. This dissipates the thermal forces that build up due to temperature increases. You will also find them protecting other track assets such as junctions or bridges from thermal forces. A key activity to do before hot weather is to inspect the blades of the adjustment switch, and most importantly, ensure the gap between the blades is correct for the temperature at the time. This ensures that there is enough space for expansion as temperatures increase, while also ensuring that the blades are properly supported. As an adjustment switch is effectively a gap in the running rail, there is a risk that if the blades are not supported properly, it could lead to a derailment. The gaps can be corrected by removing or installing rails behind the blades. Rail stress. The majority of rail track in the UK, especially on the main and high-speed lines, is CWR. This means that the rails are long metal beams, sometimes tens of miles in length, with no gaps. Metal expands when it's exposed to an increase in temperature, and rails are no different. The change in lengths can be considerable. Take a 20-metre rail length that is unrestrained. At 0 degrees, it is 7mm shorter than the same rail at 30 degrees. Now multiply that over kilometres or miles and you're talking some serious changes in length. We also need to factor in the fact that rails are not just free to expand, they are restrained at either end. This creates compressive forces in the rails as they start to try to expand, but cannot. These forces are what can lead to track buckles. So where does this expansion and the compressive forces go? The solution is to install the rails in tension by stretching them. This is known as stressing. This means the compressive forces only start to develop above a certain temperature, known as the stress-free temperature, or SFT. In the UK, the SFT is currently 27 degrees. So simply, the rail is stretched to the length it would be at a certain temperature that is defined in the standards when it's installed. However, there are times when rail gets installed without being stressed, or not to the correct SFT, such as emergencies or equipment failure. This means sections of track could act differently to an increase in temperature, or are more likely to buckle. These areas of track need to be stressed to the correct SFT before the onset of hot weather, or mitigated in another way. Joint gaps. The other main construction type is jointed track. This is formed of set lengths of rail, normally 60 foot, bolted together with fish-plated joints. These regular joints, with gaps in the rail, allow the rails to expand and contract as the temperatures change. Given the relatively short lengths of rail compared to CWR, each rail's expansion is smaller. But to allow this expansion, two things have to be correct. The fish plates holding the rails together have to be lubricated to ensure that movement is possible, and the gaps between the rails have to be set to the correct distance. Maintenance teams will survey the gaps, noting the temperature of the rail at the time, to generate what is known as a joint closure temperature, or JCT. This is the temperature at which the joint closes completely, with no further room for expansion, and thus the forces in the rail increase. If this temperature is too low, gap adjustments are undertaken to increase and regulate the gaps, ensuring uniform performance throughout the track length. Other mitigations. Rails heat up when exposed to the sun, often to temperatures higher than that of the air temperature. One way to reduce this increase in temperature is simple but effective. It is to paint the rails white. This reflects the infrared light and keeps the rail temperature lower. Painting the entire railway is not practical or feasible, so key assets such as switches and crossings, or other areas at specific risk, are painted. This might include a section of track in a cutting facing north to south, for example. It would be subject to higher temperatures as it is exposed all day to the sun, and wouldn't be cooled by a crosswind, being in a cutting. As temperatures start to rise, the maintainers have to start thinking about what work they undertake. Is it wise to be cutting into rails that might be above their SFT and therefore have large forces in them? A key area is ballast consolidation. For ballast to perform at its peak, the jagged edges should be interlocked and compacted. It gets to this state by being subjected to the forces of trains travelling over it. Digging the ballast or lifting and disturbing the track reduces the compaction or fixivity of the ballast temporarily. This reduces its resistance to the movement of the track, so the maintainer needs to decide, is the work they want to do worth the risk of the reduced ballast resistance? If the next few days are cool, then it may not be an issue, as the ballast will be compacted again by the passage of trains. But if the weather is hot, or forecast to be, it may be a bigger risk to touch the track than leave it in its current state. So now you know how track engineers prepare the track for the onset of hot weather, and about the risks hot weather poses to the railway. For more on track and railway engineering, do check out the channel for other videos, and hit subscribe. Thank you.